circuit with capacitors in parallel and in series. So here I've drawn the equivalent circuit, taking out capacitor BC that are in parallel and putting them in series with capacitor A and D. So we have our 12 volt source, capacitor A, in series with our equivalent capacitor BC, in series with capacitor D. If we're going to find the equivalent capacitance for this circuit right here, we'll use our 1 over capacitance equivalence equation equals 1 over C1 plus 1 over C2 plus 1 over C3. 1 over C equivalent, it just equals 10 over 24. C equivalent equals 2.4 microfarads, because those were all microfarad capacitors. So we can just do our math and then add our units at the end. Next, we're going to find our total energy stored in our circuit here. To do that, we just use the potential energy equals 1/2 C equivalent times the voltage squared. We just found the equivalent resistance to be the equivalent capacitance to be 2.4 microfarads. So U total equals 1/2 times 2.4 microfarads times 12 squared, and that's just going to be 1.7 times 10 to the minus 4th joules. Remember that microfarad is times 10 to the minus 6th. Lastly, we're going to find the total energy stored by each capacitor. So if you remember that for series capacitances, they all have the same charge. So for our circuit at the top here, each of these capacitors would have the same charge build up on each plate of the capacitor. And that's just going to equal QA equals QBC in this case, because we've drawn this equivalent from where these two were in parallel, equals QD. All right, to find that Q total, equals C equivalent times V equals 2.4 times 10 to the minus 6th times 12 volts equals 2.9 times 10 to the minus 5th coulombs of charge on each plate of the capacitors in our circuit. We're going to use that information to determine the total energy stored by each capacitor, and I'll show you that on the next slide. Here's that equivalent circuit drawn again with the source, capacitor A, capacitor BC, capacitor D all in parallel. We just said the charge on each of them is going to be 2.9 times 10 to the minus 5th coulombs. We have our capacitance here, and if we have the capacitance and the charge, we can find the voltage. Voltage just equals charge divided by the capacitance. So for capacitor A, that charge is going to be 2.9 times 10 to the minus 5th divided by 6 times 10 to the minus 6th, and that gives us 4.8 volts. For capacitor BC, 3.6 volts, and then lastly for capacitor D, again 3.6 volts. We can use that voltage information to find our potential energy in each capacitor, and that's just that the potential energy equals 1/2 the capacitance times the voltage squared. So for capacitor A, 1/2 times 6 times 10 to the minus 6th times 4.8 volts squared equals 6.9 times 10 to the minus 5th joules. Here we've broken B and C back out into their parallel components, and we know that if B and C are in parallel, they have the same voltage. That voltage is 3.6 volts. So we can take 1/2 times 4 times 10 to the minus 6 times 3.6 volts squared equals 2.6 times 10 to the minus 5th joules. Exact same equation for capacitor C, because they had the same magnitude as capacitor B. And lastly for capacitor D here, we have our 8 microfarad capacitor times 3.6 volts squared divided by 2 gives you 5.2 times 10 to the minus 5th joules. All right, so that's all the homework problems we had there. I hope that with the answers here and then the screencast for the RC circuit, you're going to be able to complete the unit homework for Tuesday. Look forward to seeing everyone then, and we'll go through the unit homework on Tuesday, and the test is going to follow on Wednesday. If anyone has any questions, feel free to post them here in Edmodo, and I look forward to seeing everybody Tuesday.